All right. Hey everybody, it's Elise here. I'm going to go over another structural analysis problem. Also review from statics is shear and moment diagrams. We have a cantilever. This cantilever has a distributed load of 2 kips per foot. And then we have a 10 kip load, point load, and an 8 kip point load applied at the end. Okay, the first thing of all problems is solving global equilibrium, meaning we need to solve the reactions for this. Okay, and we can do that when we have this distributed load. We need to have a point, right? When we do sum of the moments, it's going to be a force times a perpendicular distance. So we need a perpendicular distance, and we need a point load, an equivalent point load. So that is going to be right here in the middle. This is 2 kips per foot times this 6 feet, right? Those feet are going to cancel out, and we're left with 12 kips. And that is located at 3 feet, half of 6. That's where the centroid of that shape is for a rectangle. Right now, we only use that equivalent force load, point load, for solving global equilibrium. You do not use that once you get into your shear moment diagram, because the difference between having a point load right here versus having a distributed load right here is very different. It's the difference between like laying down on a 2x4 across a river, how that would deflect, versus standing directly in the middle of that and how that would deflect, right? So a point load and a distributed load are going to act differently, and they're going to cause the internal forces inside of that beam to act differently as well. Right, so now that we have that, we can do, well, I guess we'd start with drawing our reactions. I'm going to say that AY is going up, everything else is going down. My AX is equal to 0 for this one. There's no forces in the X direction. Okay, and then I have a moment reaction here, and everything else is trying to cause this thing to rotate clockwise, which means my reaction has to be resisting that movement, so it's going counterclockwise, and I'm going to call this moment reaction at A. Alright, so let's do sum of the forces in the y direction is equal to 0 is equal to, well, we have negative 12, negative 10, negative 8, plus AY. Therefore, that's what those 3 dots means. Therefore, AY is equal to, I believe that's 30. Don't ever do math in your head. Use a calculator. I've got a calculator here, but I did just look at the solution for this problem. But don't let simple math catch you up. On an exam, take the extra 3 seconds to put that into your calculator. You do not want to start off your whole problem because you thought you could add in your head quicker than you actually can. Alright, now let's do sum. So I'm going to come over here and I'm going to write 30 next to my AY. Now let's do sum of the moments. I'm going to do sum of the moments about A. And I'm going to say that counterclockwise is causing positive rotation. That's just a notation. If you put it the other way, you'll still get the same answer. It's just how you're writing out this equation. Alright, so we have positive moment reaction at A. This is why I put the R in there, because sometimes it's like moment about A. If I would have just called that M at A, then it looks a little bit confusing. So let's put the moment reaction at A. Okay, and that one's going counterclockwise, so that's positive. Then we have minus 12 times 3, minus 10 times 6, minus 8 times 10. All right, let's grab a calculator. What do we got here? 12 times 3 plus 60 plus 80, and we have 176. MRA is equal to 176, and this is kip feet. That's the unit for that. Let's just triple check that that is indeed correct. That's right. All right, cool. Got to check my work too. I don't want to make this whole video and then you have to go back and figure out what I did wrong. But also sometimes it's good to catch mistakes. All right, so let's draw. We have the global equilibrium now. Let's draw our axes for the shear and moment diagram. Always do this directly below your beam. Okay, this is a very visual tool. It's good to make sure that you do things that line up, and then we're also going to talk about trying to do things to scale as much as possible. All right, so our first thing we're going to have is we're going to have shear, V of x, and that's in units of kips for this one. Okay, shear is always going to be a force unit. Moment is always going to be a force times a distance unit. All right, and then we are going to have a moment with respect to x, and this is going to be in kip feet. Okay, this is like a very standard way of setting up a problem. Your professor will love you if you set this problem this way, if you put units on here. And what does b of x mean? What does m of x mean? It means that any x given distance across this beam, that's what the shear is. At any x given distance across this beam, that's what the moment is. So it's moment relative to an x position on that beam. That's why we're writing m of x or v of x. Okay, it's all relative to that. Okay, so let's go down to our shear diagram. And we're going to start here at 0. Right away I have a reaction popping me up 30. So come up here to 30. Now, I do not have a grid on my dry erase board, which would be amazing. But if you're doing this on engineering paper or graph paper of some sort, you know, say like, okay, maybe 3 blocks up is going to be 30. So each block is equal to 10. That's going to help you identify where your shear crosses the x-axis, where shear is 0, and then that'll also help you with where your inflection points are on the moment diagram. Now, this scale and this scale are generally going to be different. So if you look at this reaction, we have 30, and this reaction is 176. Okay, so you can't keep the scales for both of them, but you want to make sure everything on your line is somewhat proportional. So I'll attempt to do that on here. So we go up 30, and again, I said this point load is gone. We're not doing anything with it anymore, except for we want to know what is the area under that curve, which is what we just found. It's 12. Okay, so it's really the point load I should have erased, not just, okay, so this area is equal to 12. Right, so that means we are going to go down 12 over the next 6 feet. So 30 minus 12, I'm going to come over here, 30 minus 12 is 18. Put that like right here. Now how do we get there? Order of lines. Okay, we're going from a constant to a linear. So we're going to get there with a straight diagonal line, if I can draw one. Alright, now at point B, we're also popping down 10 because we have a point load there. So we're going to pop down to, it takes us to 8. We're going to come all the way over to the end. We have an 8 kip load. That's going to pop us back down to 0. So, you always start at 0 and end at 0. But if I asked you, what is shear at C? Shear at C is 8. Like, the shear there is indeed 8. It's not 0. So, whenever we say start at 0, end at 0, that's more of like we're like closing the loop. But shear at C is 8. Shear at A is 30. I hope that makes sense. I feel like that can get a little bit confusing. Right? Now, at B, shear just to the left of that point load. So 0.000 feet to the left of that point load, shear is 18. And 0.0000 feet to the right of that point load, shear is 8. So if a problem asks you, what is shear at B? It needs to also say, what is shear at B just to the right or just to the left of that point load? Okay, so make sure you're paying attention to that detail when you're doing homework or on an exam, okay? All right, so now we're going to go on to our moment diagram. I can luckily solve all of these shapes using geometry. Okay, so I'm going to break this down. Well, this is my first shape. Okay, this area is going to be, what's my height here? My height here is 12. We went down 12. Now, ignore these scales because obviously I didn't draw them very well. But we went down 12, right? So this height is 12. My base is 6. And it's a triangle, so we're going to divide that by 2. Again, that's a pretty easy one. You could probably do that in your head, but 12 times 6 divided by 2, 36. Ooh, and see, I just wrote 6. That doesn't make any sense. 36. Okay, but that's not it. We also have this area down here, which is what? It's 18 times 6 all divided by 2. So 18 times 6 all divided by 2. This is equal to 54. So my area total is equal to 54 plus 36, which is equal to 90. Right, and then over here, my area is 8 times 4. Oh, did I divide that by 2? That was wrong. That was silly. Do not divide that by 2. Why did I divide that by 2? It's not a triangle, it's a rectangle, okay? This area is not 54. That area total is not. This is just 18 times 6. 18 times 6. 108. So 108 plus 36 is equal to 114. These are the types of mistakes you're going to make on exams. And you're going to see when you get down to that moment diagram, if we would have gotten that wrong, we would not have ended up at 0 at the end. And I would have gone back. First I'd probably look at my reactions. Maybe first I should look at my areas and make sure, oh, I forgot to divide by 2, or shoot, I divided by 2 when I wasn't supposed to. That was silly. I was going too fast. Okay, so, but we caught it, because then I came over here and was like, that doesn't get divided by 2. Why did I do that over here? So 8 times 4 is 32. All right, and all of these are positive areas because they are above the x-axis. If they're below the x-axis, they're negative. So how this is working for this particular thing, your x-axis is the x distance on the beam. Your y-axis is your shear in kips. Okay, so what is the area here? We have a kip times a distance. So this is a kip foot. This is a kip foot. Convenient, right? Because that's what the area is here. Up here, if you look at this, this is kip per foot times a foot. That gives you a unit of kips. And remember that the shear is the integral of the load, and the moment is the integral of the shear, right? Which is just the area under the curve. Sometimes you can use it with geometry, sometimes you gotta do integration. All right, so I think we have everything now. So now we're going to come down here to the moment diagram. Now we have a reaction on this. So when you just have the simply supported, those supports don't resist any rotation, so you don't go directly up or directly down. But when you have a cantilever and you have a reaction there, you have to either go up or you got to go down. So Jeff Hansen is a very famous statics person. If you're in statics right now and you don't know who Jeff Hansen is, you should definitely go watch Jeff Hansen. But he has a saying of, in the kitchen, a clock is above, a counter is below. And that's how you should remember, is that clockwise moments, whether they're reactions or applied, go up on the moment diagram, and counterclockwise rotations go down. Now in my class and in a lot of textbooks, we always use this notation when we're doing like some of the moments that counterclockwise is positive. And that then gets a little bit confusing here. And then also like RISA or finite element analysis, they'll flip their moment diagrams on those softwares. So sometimes it's confusing. But aside from Jeff Hansen's, nice clock and counter analogy, some of these should be very obvious. So let's look at what is the deflected shape of this beam going to be. Okay, well, it resists moments, so we're going to go out straight for a little bit here. And then we're going to start to do something like this. Okay, that thing is sad. That's a sad guy, right? He's frowning. That is a negative moment. We have negative curvature. Okay, so I know that my entire moment diagram is going to be below here. Okay, now another thing. So that tells me I'm gonna go down for that reaction. It's counterclockwise, so Jeff Hansen tells us to go down, but also the deflected shape looks like this, so I know that my entire moment diagram is going to be in this negative area. And then the third thing is we gotta end up at 0, and all of my shear is positive, which means it's gonna pop me up. So if I would have gone up here, I would have just ended up way over here. So you don't need to remember one thing. There's a lot of clues out there to tell you whether or not, or which direction you should be going. And then with applied moments, it might not always be that obvious in the middle of the beam. In a rush and in an exam, if you don't know or you can't remember, just pick one, go to the end of the beam. If you end up at 0, you pick the right direction. If you don't end up at 0, maybe go back, flip that thing around, hopefully that's your difference. Okay, so I'm going to go down -176, right? Now I'm going to go up 144, so -176, oops, -176, oh my gosh, negative, oh, that doesn't work. Not using my calculator, but that's okay. Let's do this, let's do 0 minus 176, -176, right? Plus, use the TI 36X, that's the best calculator. I'm using a 30 right now, the buttons aren't that great. Alright, so -176 plus 144. We have a positive area kicking us back up. That takes us to -32. Now, how are we going to get there? Well, based on the order of our lines, we're going to get there with a parabola, quadratically. Okay, but we're starting here, we're ending here. How do we know if it's this or if it's this? And the answer is, this is going to be the steeper section because this is where it's larger. So you're getting more shear here at the beginning than you are over here. So this is our steeper line, so we're going to go with that one. So there's our, and that's good. We ended up with -32 because over here we have a 32. So that's going to take us back up to 0. We got a straight line, straight linear line. I don't know if that looks straight to you guys, but going back up to 0. So this is our moment diagram, shear moment diagram. Now, what if on homework or on an exam, somebody asks you for what is shear and moment at, let's see here, what do I ask for? Shear and moment, maybe I don't say. Let's just pick a point then. I don't have that on my solution. Let's do 3. So I want to know V of 3 and M of 3. Alright, so technically, we could start with writing an equation between A and B for the load, but I also can write an equation for this line right here, right? This line right here is just a y is equal to mx plus b, right? So my v, and specifically, this is an equation for shear with respect to x between A and B, okay? That does not continue on throughout here. There's a different equation for this section. Just like down here, there's an equation between A and B, and then from B to C is a different equation. That's because there's a discontinuity right there. That loading is not continuous. Okay, so my shear with respect to x between A and B is equal to, well, my B is positive 30, so I'm going to say 30, and then I'm going to say minus my shear, or my slope. Well, what is my slope there? I'm going down 12, so my rise is 12, -12, over 6x, so this is 30 minus 2x. Let's check. What is V of B? Well, that would be equal to 30 minus 2 times 6, which would be equal to 30 minus 12, which would be equal to 18. Check. We wrote an equation that when you plug in a boundary condition, so what's going on at either end, or points where you know something's going on, now we know that that equation is correct. When you get into a lot of integration, especially when we get into integrating the moment diagram to get your angle of deflection, and then integrating the angle of deflection diagram to get your vertical deflection, your actual deflection of that beam, if you mess up your shear diagram or your shear equation, you get all the way down to your your actual deflection diagram equation, you're kind of, no, you're not screwed, but it's good to check things along the way. Alright, so now let's plug in what is v of 3 equal to. V of 3 is equal to 30 minus 2 times 3, so that's 30 minus 6, so it's equal to 24 kips. Okay, there would be one answer. Alright, so now let's say, and now like that kind of lines up, right? We're right here, halfway in between. Okay, so that is 24. Now, my m of x between a and b is equal to the integral of v of x between a and b is equal to the integral of 30 minus 2x dx, which is equal to 30x minus 2x squared over 2 plus cm. This is my constant for my moment diagram. Okay, so now let's say m of 0 from a to b is equal to what? It's not equal to 0 here. It's equal to negative 176. So that would be equal to 30 times 0 minus 0 squared plus cm. Therefore, cm is equal to negative, that doesn't look like an m, 176. Okay, because that goes to 0, that goes to 0, also those 2's are going to cancel out. So now I have my m of x between a and b is equal to, I'm going to rearrange this a little bit, well, it doesn't matter, 30x minus x squared minus 176. And we want to know 3. So m of 3 is equal to 30 times 3 minus 3 squared minus 176. Let's plug that into a calculator. We have 30 times 3, that's 90, minus 3 squared is 9, minus 9, okay, minus 176. That is equal to negative 95. And this is kip foot. Now technically we didn't check this, so let's check boundary conditions. We know that m of 6, which is equal to m of b, is equal to negative 32. So 30 times 6 minus 6 squared minus 176. Let's see what that equals to. So 30 times 6, 180. 6 times 6 is 36, so minus 36 minus 176. That gives us negative 32. Check, we know that equation was correct. So now we know. We know that at 3 feet, m is equal to negative 95 kip foot. Alright, that's all I got for you guys. I hope that made sense.